Stanford University.
All right, let's move on to supersymmetry. Now, I have struggled to find a way to explain supersymmetry, and I took it as a challenge. My own opinion from looking through my notes right now is that I have failed that challenge, but I can only do my best. Supersymmetry is probably the most abstract construction in all of physics. It is incredibly abstract. Using, among other things, these bizarre Grassmann numbers, which aren't numbers at all, but which are objects which do some things that numbers can't do. On the other hand, supersymmetry is full of them, and we need to understand them a little bit. So I told you about Grassmann numbers last time. Let me just review very quickly. And then I want to tell you about supersymmetry itself. Supersymmetry is a form of symmetry, similar in some respects to other symmetries. Other symmetries might be rotation symmetry, translation symmetry, the symmetries of space-time. Supersymmetry is a symmetry of space-time, but a very, very bizarre one. And in order to make it a symmetry of space-time, one has to expand the notion of four-dimensional space-time to something radically new, really strangely new. There's that strange newness of this new kind of symmetry that I want to talk about today. Okay, let's talk about Grassmann numbers. Grassmann numbers are mathematical constructions. They can be represented by matrices, but it doesn't help very much. All right, so I will indicate them sometimes by epsilon, sometimes by theta, usually by Greek numbers. And there may be several of them in a problem, so let's label them epsilon sub I. Sometimes, when there's an even number of them, we might even group, or first of all, you can multiply them by ordinary numbers. Now, when I speak about ordinary numbers, I mean complex numbers, real or complex. So you can multiply them by I, the square root of -1, not this I over here, but the square root of -1. You can multiply them by something which is not imaginary. And in fact, you can combine them together into complex combinations. Right? If there's an even number of them, it's often the case that you'll group them in pairs and make complex combinations out of them. So for example, if there were only two in your problem, if there were only two Grassmann numbers, you could call them epsilon 1 and epsilon 2, or you could call them epsilon and epsilon bar. In my notation tonight, the bar stands for complex conjugate. That's a common notation for complex conjugate, is to put a bar on top of things, similar to star. All right? So there are these Grassmann numbers, comma, not times. There are these Grassmann numbers which have the odd property that they anti-commute. The square of any one of them is 0. It is not itself 0, but the square of any one of them is 0. And epsilon 1 times epsilon 2 is minus epsilon 2 times epsilon 1. We'll come back to that. Right? In a Grassmann algebra, there are, first of all, these anti-commuting Grassmann numbers, and we'll call those things odd. They certainly are odd, but they're odd in a sense which is mathematical also, odd versus even. The other kind of numbers in such a setup are ordinary numbers. Let's just call them n for number. These are not Grassmann numbers. They're numbers like 7, 3, -4, x plus I, y. And they can be complex, and they're ordinary numbers, n. And those are called even. Even elements of the Grassmann algebra and odd elements of the Grassmann algebra. The rule is an odd times an odd, in other words, the product of two Grassmann numbers, is an even element. That means it commutes with other things. An odd times an even, what did I say? Did I say odd times odd is even? I hope I did. Odd times odd is even. Odd times even is odd. And even times even is even. Okay? So, for example, what that means, odd Grassmann numbers always anti-commute. Epsilon with epsilon, these don't have to be the same. They could be epsilon I with epsilon j. Is always, they anti-commute. This means epsilon I, epsilon j plus epsilon j, epsilon I is equal to 0. It also means that every epsilon squared is equal to 0, because the anti-commutator of something with itself is just its square. All right, so these are the odd elements. The even elements commute, let's say nm for two numbers equals 0. This means n times m equals m times n. And the convention is that even elements and odd elements also commute. So epsilon times n is n times epsilon. The only anti-commuters are a pair of epsilons. Okay? So that's the oddness and evenness of Grassmann numbers. Yeah?
Are you making a distinction between Grassmann algebras and numbers, or is it one and the same?
Well, the elements of the Grassmann algebra are the Grassmann numbers. Right. So I'm only making the distinction between, the things which you act on are the Grassmann numbers. The rules are the algebra. Okay. Now, there's Grassmann algebra, which we've stated over here. There's the theory of functions of Grassmann variables. Okay. What is a function of a Grassmann variable? Let's say a function of one Grassmann variable. Well, one way to express that function is as a power series in epsilon. So it'll be some a, which is independent of epsilon. Incidentally, a could either be a Grassmann number or a non-Grassmann number, but it doesn't depend on epsilon. We're thinking about functions of a particular Grassmann element, epsilon. A plus b times epsilon, but nothing after that, because epsilon squared is equal to 0. Now, if there's more than one Grassmann variable, you might have a function of several of them, let's say two of them, either epsilon 1 and epsilon 2 or epsilon and epsilon bar. In that case, you would have function of epsilon 1 and epsilon 2 would begin with something which is independent of the epsilons. Then there could be, let's call it b1 epsilon 1 plus b2 epsilon 2, and then some c epsilon 1 epsilon 2. Nothing after that. Why not? Because if you multiply it by another one of the epsilons, you get 0 again. That's if there are only two epsilons in the problem. You could also write this in terms, if you made a complex combination epsilon and epsilon bar, you could write this in the form a plus, I guess we can call it b bar times epsilon plus epsilon bar times another b plus c epsilon bar epsilon. It doesn't matter whether you use the complex combinations or the real combinations. Either way, the sum terminates after c, because another factor of epsilon will set it to 0. That's if there are only two epsilons in a problem. If there are more, depending on the number of epsilon variables there are, the series will stop after some number of terms, after you've used them all up, so to speak. So there aren't very many functions. Usually, when you write a function of Grassmann variables, you assume that all the terms are either odd or even. For example, if f is an even function, a commuting function, then a would be even, b would have to be odd so that b times epsilon is even, this b would be odd, and c would be even. The other possibility is that f itself is an odd element of the Grassmann algebra. Then a would have to be an odd element, b would be even, and c would be odd. So you can have functions which are either, but nevertheless, no matter what they are, if they're functions of a finite number of Grassmann variables, the number of functions is not very big. They're polynomials and they end at some point. Okay, that's the algebra of Grassmann variables. And the functional analysis of them, well, forget the functional analysis, just the functions of them.
Yeah. Can it be used in trigonometric functions as well?
Well, you could write the sine of epsilon, but the sine function is just an expansion in powers, and so it would just end at the first sine of epsilon is epsilon. Yeah. There's just not enough structure there to make interesting functions other than a couple of polynomials. Now, there's even a calculus of Grassmann variables, both differential and integral. The notion of a indefinite integral doesn't really exist. The notion of a definite, well, yeah, the notion of a definite integral exists, or just the integral of a function of epsilon. Maybe I'll go through it the next time. I don't think I'll go through it tonight, the integral calculus of, but it's very easy to remember. Derivatives and integrals are exactly the same thing. They don't differ. But we'll come to, I won't do integrals tonight. I'll just tell you about the differential calculus of Grassmann variables. The derivative with respect to theta, sorry, theta is a Grassmann variable now. Let theta be a Grassmann variable. I don't know why I started calling it theta in terms of instead of epsilon. Yes, I actually do know why, but for the moment, no difference. Derivative with respect to a Grassmann variable of a function of a Grassmann variable is very simple. First of all, if the function doesn't depend at all on theta, for example, if it only consists of a constant, then the answer is 0. Derivative with respect to theta of a plus b, let's say theta times b, that's just equal to b. Just exactly as if you were just differentiating with respect to theta. Now, you do have to be a little bit careful. Let's suppose that this function here was an even element of the Grassmann algebra. That means A is an even element. Okay, no big deal. But it also means that B is an odd element. That means you'll have to distinguish between B theta and theta B. They're different, and they're opposite in sign. So if B is an odd element, B theta and theta B are different. If you want to differentiate with respect to theta, first bring the theta dependence to the left, and then hit it, and the derivative just gives B. That's just one of the rules of fiddling around with these Grassmann numbers. So there isn't much to the calculus of Grassmann variables either. Of course, you can ask me, what if you have a function of, let's take the derivative with respect to theta. Of a function, now this is a complex theta, of a function which is an a plus b theta plus, let's call it b plus b bar theta, b theta bar, b plus c theta bar theta. This is the generic situation if you have two thetas in the problem, and I've arbitrarily organized them into two complex pairs. You could use theta 1 and theta 2 also. Let's see what this is. The derivative with respect to theta of A is 0, so that's the first term, plus, now, we have to be careful. Is this an odd or an even function here? So let's say it's an even function, just to be specific. A is even. What is B? Odd. So that means when I hit it with respect to derivative with respect to theta, I had better bring the theta to the left. What happens when I bring the theta to the left? Minus. So the next one would be minus B bar. Now, the derivative of theta bar with respect to theta, that's 0. Theta bar is a different variable than theta. We could use theta 1 and theta 2, it doesn't matter, but the derivative of one variable with respect to another variable is just 0, so we get 0 from here. Now, what about the derivative with respect to theta of this term here? We're going to get plus c. Are we going to get theta bar or minus theta bar? Minus theta bar, because in order to hit it with the derivative, we first have to bring the c through to the other side. Okay? And that costs us a sign, so that's minus c theta bar. That's an example of a derivative operation on Grassmann variables. The only thing you ever have to remember is to reorder things so that when you differentiate, you're always differentiating something that's right next to the derivative. Okay, let me prove a little theorem, which is important.
You had minus signs on both terms.
Yeah, that's because I had, yeah. Yes? Both of these, yes. That's because you had to bring the theta through an odd element over here, gave you a minus sign, and you had to bring the theta through theta bar over here. Oh, sorry, I made a mistake. No, what did I say? Yeah, no, that's right. That's right. Yeah, if the whole thing is an even element, then C must be even. All right. Now, the whole thing could be an odd element. Let's suppose the whole thing, the whole function here, was an odd element. In that case, A would be odd, B bar would be even, B would be even, and C would be odd. Let's see what we get. To differentiate, again, differentiating A gives us nothing, but now we can bring the theta past the B bar because the B bar is an even element, and then differentiate it. So this time we will get plus B bar, not minus, and over here we have to bring theta through two odd elements to get it to the left. That will not cost us a sign. Each time we bring it through, we get a sign, but we bring it through two odd elements, no more sign, so that's also plus C theta bar. All right, so you just have to do the bookkeeping carefully. It's amazing that these things are useful. Let me give you another little theorem, yeah.
You could just easily have written a function C theta theta bar, couldn't you?
Yeah, you can just write a function C theta.
Then the signs of the derivatives of C would change.
Sorry, let's just write a function C theta theta bar. Now, what's your point?
The point is that then the sign, that if you had an even function, it would be plus C theta, and the odd function would be minus C theta bar.
Theta bar. Yeah.
So what is the significance of the way that it turns out if we could just easily reverse the terms?
C could be even or odd.
What is the significance?
What's the significance of it turning out to be
It's a bookkeeping device for keeping track of fermions, is what it is. There's no significance other than the significance we will attach to it as we go on.
I think you would change the sign of C, is what he's
In which case? If C is odd?
He wants to write the function with theta and theta bar reversed, so you just change the sign of C.
Oh, yeah, well, sorry.
parity of C.
If I change the order of theta and theta bar, then I should write minus c theta theta bar. C theta bar theta is minus c theta theta bar.
So if you reverse the order, then you just define the constant term.
It's a rule. It's a mathematical rule, a new kind of number. A new kind of number, when you switch two of the odd elements, you change the sign. If c is also an odd element and you bring something past c, you also change the sign.
But when you change the sign, you don't change its parity.
You don't change it.
It's a parity. You don't change it from.
You don't change odd to even. That's right. That's right. That's right. Any of these manipulations do not change odd to even, but they can change the sign of the object.
So I'm confused. I'm confused about something I think is minor.
Yeah.
So I'm thinking of our coefficients, A, B, and C, is drawn from the complex number field.
They could be complex numbers. If they happen to be even, if they're even. If A is even, it could be a complex number, but it could also be something else. It could be the product of an even number of epsilons or thetas.
But if we only have, if we have two of them though, then a product, then it will vanish, I would think.
If we have two of which?
If our Grassmann field, I guess it's a field, has only two independent elements.
If there are only two elements, well, you always include the numbers along with the odd elements. Right? So typically, we might have some finite number of odd elements, but all either the complex or the real numbers. Now, you can define more sophisticated things. You can define things which only have a finite number of ordinary numbers also. Just the integers modulo 5 or something like that, that would also allow you to make Grassmann algebras. The ones we're really interested in are the ones that have complex numbers and some finite number of Grassmann elements that we'll call, from time to time I'll call them epsilon, from time to time I'll call them theta.
I'm sorry, with the first case was the entire function was even, and then the second case the entire function was odd?
I guess, I don't remember.
Okay.
Yeah.
Something like that.
The two derivatives are like opposites of each other.
What's that?
The first one was beta plus c theta, negative, and then the minus, and then the second version was the opposite of that.
You want to go through it again?
No. I'm just saying, is that they're like symmetrical, these two answers? Is that a general characteristic of the stuff?
Sometimes. Sometimes, but the rules are simple. Whenever a Grassmann element goes past another Grassmann element, it changes the sign. Now, in fact, you can also think of derivative with respect to a theta as a kind of Grassmann element. But let me show you another interesting fact. But let me start with ordinary functions of ordinary variables first. Let's take just a function of a single variable and consider the differential operators derivative with respect to x and multiplication by x. Those are two operators, and they have the following property. The product, which way is it? Yeah. Let's d by dx times x minus x d by dx. Have you ever seen this thing before? It's the commutator of x with d by dx with x. Okay? You know where it occurs? It occurs in quantum mechanics. It occurs in quantum mechanics because the momentum of a particle is represented by an operator which is minus I d by dx. All right. What is this commutator? D by dx times x minus x d by dx. Well, you all know how to do it, but I'll do it anyway. You take it and you apply it to a function, any function, and you see what you get. All right, so let's begin with the first term. The first term gives us derivative with respect to x of x times f of x, and that's the sum of two terms. The first term, the derivative hits x and gives 1, so this just gives f of x. And the other term, the derivative hits f, so it's plus x times, let's call it f prime of x, where prime indicates derivative. The derivative can hit x and leave f, or it can hit f and leave x. Now what about in the opposite order? In the opposite order, we have x times derivative with respect to x times f of x. That's just x times f prime. Now the x is on the left, the derivative hits f of x, and that's just x times f prime. So the difference between these is just the difference between this and this. The x times f primes cancel, and what we find out is that this is just equal to f of x. That all can be rewritten in a simple package. The commutator of derivative with respect to x with x is just 1. Why 1? Because it does nothing. It just acts on a function and gives back the same function. So this is a simple theorem about the commutator of derivatives with multiplication by f of x. What about derivatives with respect to Grassmann variables? You might guess, and you would be right, that exactly the same thing is true, except for one thing. What is it? Anti-commutator. Let's check that out. Let's just check it out for the function a plus b theta. I'll work it for the even case. You can work it for the odd case, where a is an even element and b is an odd element. That's the case I'll do. Let's first hit it with theta d by d theta, and then we'll have to hit that with the opposite order. All right, now d by d theta when it hits a gives what? 0. How about d by d theta times b theta? B is an odd element, so we'd have to bring this around to the other side. This will give us, forget this for a moment, this will just give us minus b theta, right? Sorry, just minus b. Minus b. Minus b. But then we're going to hit it with theta again. Okay? So it's minus b theta. Theta on the left. But this is also equal to b theta. B is an odd element. I could have done this, yeah, okay, it's fine. It just gives me back b theta, right? Everybody see what I did? Yeah. Okay, good. So that's the first thing. We can erase all this. Now, what about the opposite order? D by d theta, theta times a plus b theta. Theta times a just gives us theta times a. But what about theta times b times theta? That's 0. I could bring the theta through here, and then I would have the product of two thetas, and product of two thetas is 0. So this is just equal to the derivative with respect to theta of theta times a, right? Which is a. So now supposing I add these, then I get the anti-commutator of theta with d by d theta acting on an arbitrary function, a plus b theta, gives back a plus b theta. Here's a, here's b theta. So this is 1. So for Grassmann derivatives, with respect to Grassmann variables, theta, the anti-commutator of theta with d by theta is 1, whereas for ordinary numbers or ordinary functions of ordinary variables, it's the commutator of a derivative with respect to a coordinate is equal to 1. So I showed you this for a variety of reasons, but one of them was just to show you how to manipulate these objects. And as I said, the only rule that you have to keep track of is when you pass one odd element past another one, to change the sign. Otherwise, it's just like ordinary algebra, much simpler because there's only a few functions and not very many rules, just because there isn't very much to have rules about.
Question. You discussed odd and even functions. Are there mixed functions where you're at?
You can invent mixed functions, but they're really not. Normally, you don't allow mixed functions. An expression should either be odd or even. You can investigate and start playing yourself with what happens if you have mixed functions, but normally an object is either odd or even.
Yeah, just wondering if that f of x that you've got there, I'm sorry, is that odd? Or?
No, this is just ordinary functions. Ordinary functions, even functions. I was just reminding you of something here. This is kind of the commutator of x with p, right? This could be p, or if we multiplied it by minus I, then this would be the commutator of x with p is equal to I. Leaving out h bar, yeah.
So we've talked about Grassmann numbers with like one or two multiple components, right? Is there a limit?
Is there what?
Is there a limit to it?
A limit to what? How many you can have?
How many you can have?
Oh, you can have any number. Yeah, you can have any number, but you can have any number of them. Right. All right, so that is what a Grassmann algebra, Grassmann calculus. The only thing that I didn't tell you, as I said, was how integrals work. I'm going to tell you right now. Maybe I'll work this out for you, but not right now. The integral d theta of a function of theta is the same thing as the derivative with respect to theta as f of theta. I won't tell you why right now. If it happens that we need derivatives, I will show you why it's true. Okay. It's the only rule that allows you to integrate by parts. If you insist that the integration by parts formula be true, then it's necessarily true that derivatives and integrals are the same thing. So that makes calculus very, very easy. All right, now let's review for a few seconds or a couple of minutes the idea of symmetry groups. And then we're going to come to supersymmetry. Symmetry groups. All right, so let's just very quickly review. We have some group elements. I'm interested in continuous groups now. And let's call the group elements G. G sub I. This is the ith group element. I could be, and I here just indexes whatever you want it to index. And as I showed you last time, the whole structure of the group is encoded in the algebra of commutators, the Lie algebra. It's called the Lie algebra. The Lie algebra of commutators. These G's are not, oh sorry, these G's are not the group elements. These G's are the generators of the group. The generators of the group, the infinitesimal elements, unitary group for an element very close to the identity is 1 plus I times a small number. This epsilon is not, at the moment, a Grassmann number, times G. And there are a collection of linearly independent generators. In the case of the rotation group, those generators are just the angular components of the angular momentum, the different components of the angular momentum, the L's, Lx, Ly, and Lz. For more complicated groups, there are more generators, but there's a collection of generators. And the important thing about the generators is the commutators of them. That tells you it's basically an infinitesimal version of the table of multiplication of group elements. Gi, Gj, the commutator of two group elements, what does it have to do with? It has to do with group operations about different axes, so to speak, and then undoing them, what you get left over with. We talked about that. All right, the general rule is that the commutator of two group elements or two group generators is another generator. In the standard formula, there's always an I here. And then there's a set of constants. Let's call them C. Ijk times an element gk. That the commutator of the ith and jth element, this is summed over k, of course, repeated indices, that the commutator of one generator with another is a linear combination of generators. That's the structure of all continuous groups. And these constants here, they're just numbers. They have some symmetry properties. They're called the structure constants of the group. What are they for the rotation group? Anybody remember?
The permutation symbol.
Yeah, the permutation symbol, epsilon ijk, for example. But in general, they're just a set of, they have some symmetry properties. For example, the left-hand side, the commutator is always antisymmetric under I and j. Gi commutator gj changes sign when you flip them, so it's antisymmetric under interchange of I and j. And in fact, you could discover by a few manipulations that it's antisymmetric under interchange of any two of them. But that's not important. The important thing is that the algebra closes. That means that the commutators of generators give back generators again. That's fundamental to the character of what a group is. Now, the G's typically for sensible symmetry groups are always Hermitian operators. They're Hermitian matrices. That means they have real eigenvalues. That does not prevent you from putting them together into complex combinations. Let me give you an example of one that we've studied in the past. Take the angular momentum components, Lx, Ly, and Lz. Those represent angular momentum. They're observable quantities. They're conserved in the real world. And of course, they're Hermitian because observable quantities are Hermitian. That does not prevent you from putting together combinations like Lx plus or minus I Ly. Do you remember what these things were? Raising and lowering operators. What do? They acted on state vectors with a given value of Lz, we called it m, and it either raised or lowered m by 1 unit. So I just point out to you that it's often the case that we combine them together into complex combinations for various algebraic purposes that are useful to us. All right? In putting them together into complex combinations, that doesn't change the fact that the original objects were Hermitian. Okay. One last point before we get to supersymmetry is that when you have a real symmetry of a physical system, it also implies something about the connection between the generators and the Hamiltonian. In particular, it says that the Hamiltonian of the system commutes with the generators. Commutator H with the generators is equal to 0. That's another way of saying that when the generator acts on a state, it doesn't change the energy. I think we proved that last time, that when you have a symmetry, it means that the generators, when they act on a state, do not change its energy. That's another way of saying that G commutes with H. And it also says something else. It says that the time derivative of the generator is 0 as a quantum mechanical equation of motion. It says that G is a conserved quantity. So I put those things together. I'm just reminding you of them because we're going to play that game now with generators. All the ordinary things of physics always represent physical quantities which are even elements of a Grassmann algebra. Anything you measure, when you measure it, you get a number. The number is a number. It's not an element of it's not an odd element of a Grassmann algebra. And so all the fermion fields are odd, but you never measure fermion fields by themselves. You can't measure the field of a fermion. You can only measure the square of the field of a fermion or something like that. The things you measure in nature are things which you should think of as even elements if there's any reason at all to be thinking about a Grassmann algebra, if there's any reason. The symmetry elements, rotation symmetries, all the normal symmetries of nature involve commutators. Involve commutators and not anti-commutators. Supersymmetry is a symmetry where the generators are odd elements of a Grassmann algebra, which means everything you would say about ordinary symmetries, you say exactly the same thing except you put anti-commutators there. All right, so I'm going to give you now an example. Let's invent two generators, Q. Q and Q dagger, or Q bar, doesn't matter, complex conjugate. As I said, it's sometimes profitable to combine the generators of groups into complex combinations. Supersymmetry is nicely expressed in terms of complex combinations. These are intended to be odd elements. Right? Odd elements means that the anti-commutator of Q with itself is 0. The anti-commutator of Q bar with itself is 0. The anti-commutator of Q with Q bar might be something else, just in the same way that when you have any other kind of group, when you commute two generators, you get a third generator. You may find out that when you anti-commute Q with Q bar, you get something else. Would it be an even or an odd element of the algebra? Even. All right, so I'm gonna construct for you an example. It's constructed out of fermion fields, or basically something simpler than that. I think we may have even talked about it, but I'm going to go through the details of it because it is the basic supersymmetry, the most primitive version of the supersymmetry is the most primitive version. It's related to the real supersymmetry the same way that quantum field theory is related to the harmonic oscillator. That's how primitive it is. But if you know all about harmonic oscillators, you know a lot about quantum field theory because quantum field theory is just a collection of harmonic oscillators. Same thing here, very similar. But now we have to introduce two kinds of creation and annihilation operators. We can think of them as odd and even. The even ones are just harmonic oscillator creation and annihilation operators, A plus or A minus. And I'll just remind you what the algebra of these things is. The commutator of A plus with A plus is the same as the commutator of A minus with A minus is equal to 0, and the commutator of A minus with A plus is equal to 1. That's the algebra of creation and annihilation operators. And all these are perfectly conventional harmonic oscillator raising and lowering operators. Now we'll also introduce a collection of fermionic creation and annihilation operators. Same exact rules, except anti-commutator. Commutator of two creation operators is equal to the commutator of two annihilation operators, anti-commutator, excuse me, is equal to 0. And the anti-commutator of a creation operator with an annihilation operator for fermions is again equal to 1. Okay. Incidentally, this says that C plus squared is equal to 0, and this says that C minus squared is equal to 0. Only one creation operator for fermion, only one creation operator for a boson. Okay? So we're not talking about anything as complicated as a quantum field. We could just be talking about a fermion or a boson at rest. It's either there or it's not there. Or if it's a boson, there are one of them or two of them or three of them. We're not worried about its motion, just the question, a boson at rest, how many of them are there? That's controlled by, and we can create and annihilate them, or fermion at rest. Not worried about their momentum. Okay. Now I will construct for you the generators of a supergroup, or of a supersymmetry. Let's suppose these particles have a mass m. Let's suppose they have a mass m, and the energy is just the sum of all the masses of all the particles, the mc squared. If we're interested in the energy, it's just the total number of fermions times the mass of a fermion plus the total number of bosons times the mass of a boson. If the mass of the fermions and the bosons happens to be the same, then it's just this total number of particles, fermions or bosons, times the mass of the particle. So let's call the mass of the particle m, and let's write q is equal to square root of m. That's a convention, of course. Putting a square root of m there is a convention, times the creation operator of a boson times the annihilation operator of a fermion. So what does it do? We talked about this last time, but I'll just remind you. It removes a fermion if there's one there, and it replaces it by a boson. So it's a thing which takes a fermion and makes a boson out of it. Likewise for this one, except not quite likewise, square root of m times a minus c plus. Oh, I forgot to write down something. We didn't discuss the commutators of the a's with the c's. The a's are even, the c's are odd. The rule is any a, whether plus or minus, commutes with any c. They all commute among themselves. All right, so that means in particular that it doesn't matter which order. You can take this odd element, the c's are odd elements, and bring it past the even elements, doesn't matter. Likewise here. These are the generators of the supersymmetry algebra. Right? What do we want to do? I would like to know what the anti-commutator of q with q bar is. That's the analog of knowing what the commutators are for group elements. They tell you the structure of the group. So let's see if we can figure out the analog here for these supersymmetry operations. And as I said, what they do, they don't rotate things in space, they don't translate things in space, they simply take a fermion and replace it by a boson or vice versa. But let's work out the anti-commutator. Let's work out the mathematics of them. It's fun, and it's not very hard. Okay, anti-commutator, it's not hard, but if I try doing it in real time, I will surely make mistakes and stand here puzzled, so I'll use my notes. Okay, anti-commutator of Q with Q dagger. What is that? Well, first of all, it has an M in front of it. A Q times a Q dagger will have an M. Q and Q bar, the Q dagger and Q bar are the same thing. No difference. Q and Q bar. That will have M, and then it will have Q, first of all Q, which is A plus C minus, that's Q, and then Q bar should be A minus C plus. That's Q times Q bar, but now I have to add Q bar times Q in the opposite order. So I will add here plus, not minus, because we're talking about anti-commutators. The opposite order, A minus C plus times A plus C minus. Whoops, that's it. That's the anti-commutator. This times this plus the opposite order. Okay, let's work on it a little bit. It's not very hard. First of all, you can take the A's past the C's, right? You can pass an even element right past an odd element. It costs you nothing. So we can write this as M. I just want to put all the A's together and all the C's together. A plus A minus times C minus C plus. And then over here, it's plus A minus A plus C minus. Okay, so far, nothing very interesting about it. But now let me add and subtract something. Now here's where I got to do it carefully. Let's add inside the bracket, plus, let's get it right, A plus A minus C plus C minus. But now I've added it. I'm not allowed to just go around adding things. I've got to subtract it. So minus A plus A minus C plus C minus. Okay, now let's look at the terms. First of all, this plus this. Both of them contain A plus A minus, so that factors off. But then what does it multiply? It multiplies C minus C plus C plus C minus. What is that? That's the anti-commutator of C plus with C minus, right? Well, what is that? 1. So the C plus C minus, the C minus C plus and the C plus C minus add together, making 1. And this thing, first of all, contains M times, it looks like it's got twice A plus A minus, right? Agreed? That's the first term. Now what about this term? This term has C plus C minus and C plus C minus again. But it has A minus A plus minus A plus A minus. So what does it have? It has the commutator of A minus with A plus. What is that? 1. So this comes down and adds plus C minus. All times twice M. Somehow I, Say it again. Oh, no 2. There's no 2, is there? No, where did I get? No 2. No 2. No 2. No 2. Good, because I hated that 2. Okay, what is A plus A minus in harmonic oscillator language? It's the number of bosons. What is C plus C minus? It's the number of fermions. So we can write that this is equal to the mass of times the number of bosons plus the number of fermions. Now notice I have assumed that the mass of the fermions and the bosons is the same. I've assumed that. We'll explore a little what would happen if I didn't assume that. All right, then I wouldn't have gotten, I would have gotten whatever I got here. What is this expression here? We're talking about particles, we're not thinking about the motion of particles, we're talking about particles at rest. For a particle at rest, its mass is equal to its energy, right? So this is the mass of a particle times the total number of particles. It's the total energy of the system, and we can either call it the energy or the Hamiltonian. So here's what we've discovered. We've discovered that the anti-commutator of Q with Q bar for this simple system is the Hamiltonian. Now, first of all, the Hamiltonian is an even element. Is the Hamiltonian a generator of a symmetry group? Yes. It's the generator of time translations. Time translations are a symmetry of systems with time translation invariance. And the Hamiltonian is the generator of time translations. All right, let's finish up the group. We have to find out, what we've discovered is that the Q's by themselves are not enough to form a closed algebra. When you anti-commute the Q's with themselves, you get back the energy or the Hamiltonian. What happens if you anti-commute a Q with a Q, incidentally? That's just Q squared. That's just Q squared. Where is Q? Go up to the top. Q squared will have two C minuses. Two C minuses. Q squared will have A plus, C minus, C minus. But C minus squared is 0. So the anti-commutator of Q with itself is 0. The anti-commutator of Q dagger with itself is 0. 0 is okay on the right-hand side of a commutation relation for a group. All right. What about, what's missing? What haven't I, which pieces of the algebra haven't I considered? H with Q, right? By anti-commuting Q with Q, we found out that it's got to contain the Hamiltonian. Now, this is very odd that the symmetry group not only contains these operations which take fermions to bosons, but it also contains the Hamiltonian, which means time translations. Very interesting. Okay, what about Q with H? I'm not going to do it on the blackboard. I'm going to leave it for you as an exercise to do. All you have to do, here's H, commute it with Q, but I'll just show you an easy way to think about the answer. Q with H is 0. Anti-commutator of Q with H is 0. Not because it's an odd or, sorry, not anti-commutator. You don't anti-commute odd with even. You commute odd with even. The commutator of Q with H. Happens. H is even. H is even. H is the energy. You wouldn't like a system whose energy was a Grassmann variable. No, not good. Okay. Happens that this is 0. Now it would not be 0. I'm going to show you why in a moment. It would not be 0 if the masses of the bosons and the fermions were not the same. So let me show you how you can see that it's 0 if, and actually only if, the mass of the boson is the same as the mass of the fermion. We've done this sort of manipulation many times. You take QH minus HQ, and you act on any state which has a definite energy. Any state which has a definite energy. Okay? Whatever. Okay. What does Q do? Q either removes, I can't remember, does Q remove a fermion and replace it by a boson? Or the other way? Whatever it does, it takes one particle out and puts another particle in of exactly the same mass if the masses are equal. Assume for the moment that the masses of the bosons and the fermions are equal, then what's the energy of the state that you get when you act with Q on a state of definite energy? Same energy, because you've just taken one particle out and put another one back in, but a particle of the same mass. Okay? So this must equal H acts on QE. That just gives me E minus E times QE. Why? Because Q times E is an eigenvector of the energy. On the other hand, what about QH on E? What does it do? Well, H acts on E to give just E. In other words, it just gives us Q times E times E. These are the same. Cancels. That's always true anytime you have an operator which acts and doesn't change the energy of a state. It always commutes with a Hamiltonian. Things which commute with the Hamiltonian are things which, when you act on states, don't change the energy. This object, as long as the bosons and the fermions have the same mass, then Q does not change the energy of the state. And if that's the case, then Q commutes with the Hamiltonian. What if the two particles didn't have the same mass? No, then it just wouldn't commute. And you wouldn't have a nice closed algebra here. You get something else on the other side here, which would eventually make a mess out of it.
Can we go back just a moment before you erase that? Boom.
Too late, but go ahead. If you ask the question, yeah. You want me to put it back?
Just a moment.
Okay.
That thing referred to the fact that you started off assuming E was an eigenvector of H.
Yeah.
And you said that because of that, QE is also an eigenvector of H with the same energy.
Right.
Same energy, okay.
That's the point. I'd like to just do it again. I didn't quite get it.
I think I wasn't very complete about the argument. Let's do it again. QH minus HQ acting on any eigenvector of the energy. Okay? Any eigenvector of the energy. Okay? Why does Q on E have the same energy?
It's the same energy because it replaces a particle with one energy
with exactly the same
energy.
Right. Okay? So Q times E is an eigenvector of H.
Because
it has the same energy.
And must stay, okay, and it's...
If E is an eigenvector of the energy, it means it has a definite energy. It's an eigenstate. Now Q times E has exactly the same energy. Can't have an indefinite energy. All right? So it's an eigenvector of H with the eigenvalue E. And so we can write that H over here can just be replaced by E times QE. Okay? Over here, this time it's even easier. H acts on E to give E times E, right? And it'll give us the same thing. It'll give us QE times E.
Well, I think that the simpler way, or the way I thought of it when you said it the first time was that once you decide that you have another eigenvector of the same eigenvalue, you can replace the operator with the eigenvalue.
Exactly.
And eigenvalue,
Yeah.
I mean, scalars.
That's right. That's right. I just was being a little bit pedantic. But here you see, and of course, E is just a number, so it can go past Q, that doesn't matter. And this is equal to 0. Now, there's one other element of the argument here, which I didn't make, which I will make now. This is true for every eigenvector of the energy. And if the eigenvectors of the energy are a complete basis of states, then if an object, let's just call it K for object, if it acts on a complete set of states, every state in a complete set of states to give 0, there's only one conclusion: k is equal to 0. So anything which gives 0 on a complete set of states gives 0. So if the eigenvectors of the energy are complete, which they normally are, then it follows that commutator of q with h must be equal to 0. That also says that q is a conserved quantity. It says that q is a conserved quantity, but it's an odd element of the algebra. It has an odd number of fermions in it. It's a new thing. It's a thing we haven't seen before. And what was also true that we haven't seen before is a group of symmetries which takes one kind of particle to another. When you commute them, you get something which, in this case the Hamiltonian, has to do with symmetries of space-time. Okay? Symmetries of space-time. It mixes up internal symmetries which change particles one into another with the energy which is the generator of time translations. So this is something entirely new that, well, of course it's not entirely new. It goes back to 1972 or 73 or something like that, but it is rather unusual. That's called a supersymmetry. Now there's another way to think about it, which is even more exotic. And the more exotic, this is fairly exotic, but it gets more exotic. The more exotic way is to say that there are new dimensions of space-time. Now in the simple example we're doing here, there is no space, there's only time. There's only the energy, there's no position where we put the particles, there's no translation symmetry, there is time. Why is there time? Well, if there's energy, there's time. Let me just remind you what the connection between the Hamiltonian and time is. What is the connection between Hamiltonian and time?
Partial t.
But it's the derivative, right?
Yeah. We can write it in two ways. We can write that the time derivative of a state vector, I think it's I times the time derivative, is the Hamiltonian times psi. In fact, that's one of the definitions of the Hamiltonian. It's the thing which you act on a state to shift the time. Another way to write the same thing, this is in the form of an infinitesimal shift or a differential shift of time, but if you want to shift the time by a non-differential amount, you write that e to the minus I h. Now let's shift the time by an amount delta. Delta. I'm not going to call it t, I'm going to call it delta because later on I'm going to want it to be a small amount. That's on psi is equal to psi at time t is equal to psi at what? T plus delta. The relationship between these two is just to expand, is just to, you shift by amount delta by differentiating, and if you expand out this e to the minus iht for small delta, you'll get something proportional to h. So these are really the same statement, that whenever you have a Hamiltonian, you have a rule for updating state vectors, translating them in time. So this is odd. It says that the anti-commutator of two of these supersymmetry generators amounts to a small translation in time. It's mixing up space-time with identity of particles, operations which mix one particle to another. We've seen operations that mix one particle with another. For example, the symmetries of color or isospin. They mix the protons with neutrons, for example. Isospin symmetry takes a proton into a neutron. Right? Color symmetries take red quarks to blue quarks and so forth. But nothing you ever do with them, no combination of those symmetries ever shift time or shift space. They have nothing to do with space and time. They just shifted red to blue to green, or up quarks to down quarks, but never anything to do with space-time. Here we're finding some kind of very unusual symmetry, which when you anti-commute two q's, you get a small shift of time. There is a way to think about this where the supersymmetry generators are shifts, just like the Hamiltonian itself, are shifts of coordinates, but not ordinary coordinates. What kind of coordinates would you guess? Grassmann coordinates. Grassmann coordinates. So one way of thinking about supersymmetry is to increase the number of coordinates of space-time. Now, in this example, there's only time, so space-time is just time. I'm going through in detail a very, very simple supersymmetry example just to show you how it works. But let's go a little further. Let's suppose we have some function. It could be the wave function of something, or it could be a field operator of some kind. Let's call it psi. If it were just psi of x, I would say it was the wave function of a particle as a function of its position. Right? But I'm not going to have psi of x. I'm going to have psi of theta and theta bar. And of course, it's also going to be a function of time. We could also put x in here, but we won't for now. This is the wave function to find some kind of strange superparticle located at Grassmann coordinates theta and theta bar. Now, of course, that's the most bizarre thing you've ever heard of, and it's very strange. Okay. Let's imagine some symmetries. The first symmetry is going to be good old time translation. Good old t goes to t plus, I don't know, delta. What's the and of course, what happens to psi when you shift t a little bit? In other words, what's the change in psi when you shift t a little bit? Well, psi of theta, theta bar, and t goes to psi of theta, theta bar, t, plus the derivative of psi with respect to t times delta, right? You shift t a little bit, that differentiates it and multiplies it by delta, right? Ordinary stuff. This is still theta and theta bar. You've done nothing to theta and theta bar. And if you like, you can remember that the derivative of psi with respect to t is related to the Hamiltonian acting on psi with an I. So this has to do then, if I multiply and divide by I can write this as the operation of the Hamiltonian on psi. All right. This, of course, is a symmetry of any good quantum mechanical system, time translation invariance. And I haven't done anything except tell you what a shift of time does to a function of time. But now there are other symmetries. If these were x's and not thetas, you might have space translation symmetry. They would be associated with derivatives of psi with respect to space. The question comes up, is there any kind of symmetry which has to do with shifting the thetas? Is there any notion, any kind of possible mathematical notion of a function which is a function of time in thetas, but where a shift of theta has some nice, interesting mathematical meaning? So we're going to invent symmetries where theta goes to theta plus epsilon. Now, theta is an odd variable of a Grassmann algebra. So is epsilon. Otherwise, you wouldn't be allowed to do this. We might also allow theta bar to do something. For a moment, let's just leave theta bar out of it. And also at the same time that we shift theta, we're going to shift t a little bit. T is going to go to t plus what? I theta bar times epsilon. Now, that is a very weird thing to write down. Okay? This, at least this is an even element. Theta and epsilon are both odd elements. At least this is an even element and time is an even element. But what on earth can this mean? Right? It's a very odd thing to write down, but let's pursue it a little bit. Let's see if we can find out what the generator is which does that. What happens to psi when you shift theta a little bit? I'm not going to shift theta bar, I'm going to keep it simple. Just shift theta a little bit and shift time by the same amount. What happens to psi? Psi goes to psi plus the amount that you shift theta by, let's call it epsilon, times the derivative of psi with respect to theta. That's just a formula that when you shift an argument of a function by a small amount, you differentiate with respect to the argument and multiply by the amount that you shift. And then we're also shifting time, and we're shifting time by this amount here, so let's write it down. It will give us, I think it's a minus if I kept track carefully of all the odd and even elements. Epsilon theta bar d psi by dt. Now what have I done here? I've said I've shifted time a little bit, so that means psi must shift because of the shift of time. How much does it shift? It shifts by d psi dt times the amount that I shifted the time. I think there should be an I here, if I'm not mistaken. This doesn't make any real sense, obviously, in any kind of normal mathematics, but we're following our nose and seeing what we get. Here's what psi is. Here's how psi shifts. Let's factor epsilon out of it. Let's factor epsilon out of it. Here's what we get. If we were just shifting time, we would call the coefficient here of the small shift, we would call it the Hamiltonian acting on psi. All right? Let's factor psi out of this and think of this as an operation acting on psi. It's an operation acting on psi. Let's give it a name. Let's give this operation a name. Differentiating with respect to theta, that means shifting this abstract, this very, very abstract additional coordinate, and at the same time shifting time by an amount proportional to theta bar. Let's give that operation a name. It's a generator of something. It's a generator. It's an infinitesimal generator of something. Anybody got a suggestion what I should call it? How about Q? It's an odd element because it's a derivative with respect to theta, and it's got a theta bar here. Let's call it Q. Q bar, as I said, I think there's an I here. Q bar is its complex conjugate. It has derivative with respect to theta bar. It has a theta here and probably a change of sign of I. So in the same way, you can invent a Q bar, which is just its complex conjugate. And guess what happens if you take Q and Q bar and anti-commute them? Can you guess what happens? Let's write it out. Let's take Q and Q bar and anti-commute them. So we have the anti-commutator of d by d theta is it minus? I think it's minus I theta bar d by dt the anti-commutator of that with d by d theta bar, I'm not going to try to be careful about the signs. I'll screw them up. Let's just guess I theta d by dt. Let's see if we can figure out what we get. The anti-commutator of d derivative with respect to theta and derivative with respect to theta bar, I didn't tell you what that was, but can you guess? Anti-commutator of two derivatives of theta is very much like the commutator of two ordinary derivatives. It's 0. Commutator of ordinary derivatives is 0. Commutator of two different derivatives with respect to Grassmann variables is also 0. So this term here gives us 0. What's the anti-commutator of theta bar with theta? It's also 0. Anti-commutator of any odd element with any odd element is also 0. And the derivative with respect to theta, the t here, that just goes through for the ride. It doesn't change anything. So the anti-commutator of this one with this one is 0. But what about the anti-commutator of this with this? It contains the anti-commutator of d by d theta with theta. What is that?
Hamilton.
No, just d by d theta with theta. We worked that out.
It was what?
1. All right? What about the anti-commutator of theta bar? Well, that's theta with theta here, and then there is theta bar with d by d theta. Both of them give 1. What's the net result? The net result is I d by dt. Is I d by dt. The full anti-commutator here, it looks to me like there's a factor of 2 that I screwed up. Somewhere's in here I should have a factor of 2. I don't know where it is. Probably in the definition. Probably the definition of this should be a half of q or twice q. Not important. The anti-commutator of this with this is just minus I think it's minus I d by dt. What is minus I d by dt? H. So here's a representation of q and q bar, not in terms of creation and annihilation operators, but as operations in a fictitious new kind of space-time that involves anti-commuting coordinates. It's the generators of a symmetry transformation which shifts time at the same by a very peculiar amount, theta bar times epsilon, while you shift theta by amount epsilon. The upshot of this is there's a symmetry structure. There's a geometric structure here. There's a generalized kind of geometric structure involving spaces which contain not only ordinary coordinates like x and t, but which contain these Grassmann coordinates, which are very hard to get your head around. But motion, moving around in this space, first of all entails moving around in the x's and t's. The generators of those transformations are just momentum and energy, just as you would expect, but also transformations which move you around in this theta space. And those transformations are the supersymmetry generators. That's called superspace. The symmetries are called supersymmetry, and the space, this generalized space where you think about fields and functions and so forth, in this way, it's called superspace. Now, I'm going to stop here because I think I've probably flooded you with information.
I'm sorry, right. The conclusion of that thing is equal to, you said it a lot, but I didn't.
Within a factor of 2, it's 2 and minus, it's I d by dt. All right? It comes from commuting d by d theta with theta and getting the I d by dt from here, and then anti-commuting theta bar with d by d theta bar, which gives you another 1 times d by dt.
Is it used somewhere that epsilon is small? I would see where.
Well, epsilon is an anti-commuting parameter. Its square is 0. So anything to second order in epsilon is always 0. Right. So you always get to think of anti-commuting things as small. Right. Right. That's a good question, but that's enough. I'm going to stop here because this is a lot of information. But the upshot of it, as I said, is supersymmetry, first of all, is a symmetry which takes fermions to bosons. It can be represented rather simply just in terms of operations which replace fermions with bosons, but exactly the same algebra, exactly the same. The unusual thing here is that the operations close only if you include the Hamiltonian. That's telling you that somehow the symmetry operations contain not just the mixing up of fermions and bosons, but when you do it once and then you do it twice and you anti-commute them, you get a translation in time. That's made completely manifest here by saying there's extra dimensions. The extra dimensions include these anti-commuting dimensions, and the supersymmetry generators are sort of translations in the theta space together with certain translations in time. So it's a rather marvelous structure. It gets even more marvelous when you make curved space out of it, curved superspace, and when you make curved superspace general relativity, which is called supergravity. It's a rather spectacular structure. And as I said, it's somehow an extremely deep generalization of ordinary space-time. Whether it will turn up an experiment is another question. I think we'll quit for now because to go on, we're going to go on, but we're going to go on and spend a little more time on the mathematics of supersymmetry. But for the time being, I think that's probably enough.
I don't think you failed tonight. It's making sense.
Okay.
So is the way of thinking about that start with a well-defined state, you have a well-defined state, in the middle you have this crazy stuff that sort of passes out now. It doesn't make any sense.
Well, in one sense, it's just a bookkeeping device for keeping track of fermions and bosons. In another sense, it seems to be much, much deeper than that.
For more, please visit us at stanford.edu.